Open the pod bay doors, Hal.
I'm sorry, Dave. I'm afraid I can't do that.
What would you do with a brain if you had one?
Do? Why, if I had a brain, I could...
Miles per hour.
I could while away
46, 56 degrees.
So I work with 3 generations of NASA's Mars exploration rovers. The first generation was the Opportunity rover, and that rover has been driving around Mars for 13 years. That was a rover that was designed to last for 90 days. So going more than a dozen years is an incredible success, and I'm fortunate to still be part of that mission. This big, beefy rover that's behind me here is the test bed rover, so an identical twin that lives here on Earth of the rover Curiosity that has been driving around on Mars for 4 years. And that mission is one that I was fortunate enough to be a part of from the day that it landed. So I started my postdoctoral research at the California Institute of Technology in the Jet Propulsion Laboratory in Southern California just a couple of months before this rover landed. So I got to be part of that really visceral, exciting experience of being in the room and feeling that tension when there is something exciting happening in space. And that is something that I really see relived when I watch Apollo 13. So I'll tell you a little bit about the parallels there. I'm also part of a new rover mission that is just being built now. This is called the Mars 2020 mission. It's going to get a sexier name later, but right now it's launching in the year 2020, so we just call it Mars 2020. So, Apollo 13 is all about the danger of getting back to Earth. That is the big challenge, is getting those 3 astronauts safely back to Earth, getting them around the moon, getting them a safe landing. On our rover missions, they don't come back to Earth. Every rover that we've sent to Mars has been sent there to die on Mars. And someday there will be velvet ropes around each of our long-defunct rovers on the surface of Mars, and those will be part of the Smithsonian Museum on Mars. So the drama for us who work with robotic Mars missions is not the return, but getting there. And getting to Mars is really tough. And there's several reasons for that. One is that Mars is incredibly far away. So just to give you an idea of the distance between the Earth and Mars that our spacecraft have to travel before having a safe landing, I'd like to do a little demo, and I'm going to need 3 volunteers. The 3 people who are willing to pop up here. Number 1, number 2, one more person. Number 3, okay, please give them a hand. And come up here, please. All right, sir, I'm going to ask you to be the Earth. Now, this is a plush globe of Mars, but we're going to pretend that this is the Earth and this is the size of the Earth. Okay, so please stand at that corner of the screen. You are going to be the moon. Now, if that is the size of the Earth, then this is going to be the size of the moon. So everyone's going to need to give her some help and tell her how far or how close she needs to be from the Earth. Oh, some people say closer, some say too far. What do you think? Give her some claps when you think she's in the right spot. Okay, that was some tepid applause. Clearly some disagreement in the audience here. Let me show you how far you need to be. So moon, come a little towards me. A little more. A little more. Little more. Keep coming. Keep coming. Stop. Okay, if that's the size of the Earth and that's the size of the moon, this is how far apart they need to be. All right, we've got a 3rd volunteer here. You are going to be Mars. Okay, where do you need to go? Oh, she's still going. Okay, you are as far away as you can possibly get from the Earth, and you are still way too close. At this scale, you need to be about 1.4 kilometers away. So that is almost all the way up the hill to Western. That's about the distance between here and Zwanich Park, by the way the crow flies. So really, really far. Now imagine you're a spacecraft. How big is a spacecraft compared to the size of the Earth there? Minuscule, like a little dust mite, if that. So that has to go from that planet all the way up the hill to Western Washington University and hit something smaller than that planet. So these distances are incredible, and it takes about 7 to 9 months for our spacecraft to travel between Earth and Mars. All right, thank you, volunteers. Let's give them a hand. So getting to Mars is hard because it's really far away. Hopefully you all took that away from that demo. The other reason why getting to Mars is hard is because there is very little atmosphere. So the moon has no atmosphere. The Earth has a decent amount of atmosphere. And Mars has about 1/100th the atmospheric thickness of the Earth. So that's not really enough air to slow down a spacecraft that's coming in at about 14,000 miles an hour. But it's just enough atmosphere that a spacecraft coming in at those speeds will burn to pieces from the friction of interacting with that atmosphere. So it's not enough atmosphere to help us, it's just enough atmosphere to make things really difficult. So when Curiosity landed on Mars, the NASA engineering team had to come up with a completely new way to get 2,000 pounds of spacecraft safely onto the surface of a planet 100 million miles away. So to give you a sense of that drama, I want to show you a video that the NASA Jet Propulsion Laboratory made about the landing technique that was used for Curiosity.
When people look at it, it looks crazy. That's a very natural thing. Sometimes when we look at it, it looks crazy. It is the result of reasoned engineering thought, but it still looks crazy. From the top of the atmosphere down to the surface, it takes us 7 minutes. It takes 14 minutes or so for the signal from the spacecraft to make it to Earth. That's how far Mars is away from us. So when we first get word that we've touched the top of the atmosphere, the vehicle has been alive or dead on the surface for at least 7 minutes.
Entry, descent, and landing, also known as EDL, is referred to as the 7 minutes of terror because we've got literally 7 minutes to get from the top of the atmosphere to the surface of Mars, going from 13,000 miles an hour to 0 in perfect sequence, perfect choreography, perfect timing, and the computer has to do it all by itself with no help from the ground. If any one thing doesn't work just right, it's game over.
We slam into the atmosphere and develop so much aerodynamic drag. Our heat shield, it heats up and it glows like the surface of the sun. 1,600 degrees.
During entry, the vehicle is not only slowing down violently through the atmosphere, but also we are guiding it like an airplane to be able to land in a very narrow, constrained space. This is one of the biggest challenges that we're facing, and one that we had never attempted on Mars.
Mars is actually really hard to slow down because it has just enough atmosphere that you have to deal with it. Otherwise, it will destroy your spacecraft. On the other hand, it doesn't have enough atmosphere to finish the job. We're still going about 1,000 miles an hour. So at that point, we use a parachute.
The parachute is the largest and strongest supersonic parachute that we've ever built to date. It has to be able to withstand 65,000 pounds of force, even though the parachute itself only weighs about 100 pounds.
When it opens up that fast, it's a neck-snapping 9 Gs.
At that point, we have to get that heat shield off. It's like a big lens cap blocking our view of the ground to the radar. The radar has to take just the right altitude and velocity measurements at just the right time, or the rest of the landing sequence won't work.
This big, huge parachute that we've got, it'll only slow us down to about 200 miles an hour. And that's not slow enough to land. So we have no choice, but we've got to cut it off and then come down in rockets. Once we turn those rocket motors on, if we don't do something, we're just going to smack right back into the parachute. So the first thing we do is make this really radical divergent maneuver. We fly off to the side.
Diverting away from the parachute, killing our horizontal velocity and our vertical velocity, getting the rover moving straight up and down so it can look at the surface with its radar and see where we're going to land. And we head straight down to the bottom of a crater, right beside a 6-kilometer high mountain.
We can't get those rocket engines too close to the ground, because if we were to descend propulsively with our engines all the way to the ground, we would essentially create this massive dust cloud. That dust cloud could then go and land on the rover. It could damage mechanisms and it could damage instruments. So the way we solve that problem is by using the sky crane maneuver.
20 meters above the surface, we have to lower the rover below us on a tether that's 21 feet long, and then gently deposit it on its wheels on the surface.
As the rover touches down and is now on the ground, the descent stage is in a collision course with the rover. We must cut the bridle immediately and fly the descent stage to a safe distance from the rover.
That video still makes me nervous, even though I know that it worked 4 years ago. But that is the same landing technique that NASA is going to be using to land the next rover on Mars in 2020. And a version of that technique is what NASA is planning for the first human mission to Mars, which is currently being book-kept for the mid-2030s, so about 20 years away. So those of you who are in high school or college now, you are going to be in the prime age group of the astronauts in that first class to go to Mars. Now, don't get your hopes up too much, though, because ever since the Apollo era in the late 1960s, NASA has been saying the first human mission to Mars will be in 20 years. So we've heard that before, but I think we're really the closest we've ever been. So in that video, you saw some of the lead engineers of what's called the EDL team, that's Entry, Descent, and Landing. And those are the engineers who were in the control room, jumping up and down, screaming on landing night when their spacecraft successfully landed on the ground. And there's a lot of people you didn't see in that movie. Here's a group shot of the Entry, Descent, and Landing team for the Curiosity rover. And this team is one of hundreds of teams of this size or larger that were part of the huge effort of designing the spacecraft, getting the spacecraft tested here on the ground, getting the spacecraft built and launched, designing the spacecraft landing system, and creating the plan for what the science is going to do. So I'm on the science team, and the science team for the Curiosity rover is about 400 people. So this is a huge effort. Many thousands of people have put their effort over a decade of work to get this rover onto the ground. And just take a look at the folks in their blue landing night shirts here, and take a look at their faces and compare this group to the group that was in control of getting the Apollo missions safely onto the surface of the moon. There's some differences there. NASA's come a really long way, and we do not have a space program anymore that is entirely fueled by a room full of only white men. So there are a lot of people who don't look like this working behind the scenes on the Apollo program, and I'll encourage you to come back in June for the screening of Hidden Figures, which shows the hidden story of some of the African-American women computers, mathematicians who helped get the Apollo missions to the moon. But keep in mind, when you look at the gentlemen in their black pencil ties and their short-sleeve white shirts and their pocket protectors full of pens and pencils and slide rules, how far NASA has come from what you're going to see in Apollo 13. Really, the only women that we see in the movie are astronauts' wives or guests, VIPs, who say somewhat ditzy things. So NASA today is a much different scene. Now, the control room for the Curiosity mission looks like this. This is the science control room. And this is a shot of members of the science team and some of the lead engineers creating the first plan for Curiosity the night that it landed. So that shoulder that you see in the lower left, that is me. My role as a new postdoc on the mission was to be the documentarian for Curiosity. So I was a glorified note taker. And since then, I've worked my way up to be what's called a long-term planner, which is one of the people who thinks about the longer-term vision for Curiosity, what the rover is going to be doing next week, next month, and then the next years of the mission. So every day on the Curiosity mission, this team is assembled. For the first 90 days of the mission, this team was entirely housed at the Jet Propulsion Laboratory in Southern California. But now we've all gone back to our lives, moved on to other things, and this room is largely empty, but there is a telephone line that this same number of people calls into every day to make the plan. So I call into this room from my office in the Environmental Sciences Building up on the hill in Western Washington and talk with my colleagues from New York State, from London, from Moscow, some in Australia, and it's a huge effort of scientists working remotely to create a coherent plan for what the rover is going to do tomorrow. One of my favorite things about being part of this mission is that at the end of the day, when the science plan is approved, when we have a list of things we're going to tell the rover to do that we all agree on, there is a go, no-go call. And you will see that for the countdown before Apollo 13 launches in the movie. And we go through that sequence of each roll getting called and everyone saying go or no go. So being able to say go for a real NASA mission is something pretty cool about my job. So I mentioned that Mars is incredibly far away. It takes signals that we send via radio wavelengths from Earth to Mars. It takes about 8 minutes on average for our signals to get there. So what that means is that there's nobody with a joystick at NASA driving the rover. If we were doing that, we could drive the rover off the side of a cliff, and we wouldn't even know it until 8 minutes later when the rover sent us its death beep. So we can't operate the rover in what's called real time, just because of that delay. There's a short delay between the Earth and the Moon, but if you picture the width of this screen as the distance between the Earth and the Moon, and the distance between here and Western Washington University as the distance between Earth and Mars, you can get a sense for how long that delay is. So instead of commanding the rover with a joystick in real time, what we do is that we make a list of commands to send the rover every day. So we send the rover a list of commands at the end of our day, and when the rover wakes up tomorrow, it will have downloaded all of those commands and it will know everything that it's going to do that day. So the rover will say, oh, I've got my command series. What am I going to do? 8:30 a.m., right after sunrise, I am going to turn on my heaters. And I'm going to heat these instruments and all my moving parts for about an hour and a half before I move anything, because it's so cold, if I move, I'll be too brittle and break. Then, once I'm nice and warm, I'm going to turn my head 17.9 degrees to the right and take a picture of that rock that the scientists think is interesting over there. Then I'm going to reach out with my arm, I'm going to drill into this rock, I'm going to flip my arm around and take a microscopic image of that rock. Then I'm going to retract my arm and drive 10 meters in that direction. So all of those commands for a full day of the rover get sent every day. And at the end of the day, the rover transmits a big block of data back to Earth. And then we look at that data and say, okay, yep, it took the picture over there that we told the rover to. It drove the 10 meters over there, but oh, it stopped maybe half a meter short because it sensed there was a big rock in front of it. So we analyze all of that data that comes down, and the next morning, we do it again. So here's what a day of working on Curiosity looks like. And this is a real meeting schedule for yesterday on the mission. And every colored block that you see here is a meeting time throughout the day. So you can see that our day is packed with meeting after meeting. And some of the scientists get to create the plan and go home a little early, but the engineers who actually write the code that gets transmitted to the rover, they need to stay through the bitter end, through every meeting, and the very last one here is the CAM meeting. And why we have so many meetings is for redundancy, so that we have everything we're going to tell the rover to do is double-checked, triple-checked, quadrupled checked, and so on and so on. We have multiple sets of eyes looking at every single command, making sure that if we want to use the laser at something over here, that we have people going through multiple checks to make sure that the arm is not going to be in the path of the laser. We're going to make sure that we are not going to move the camera too far so that it snaps any of its wiring on the interior of the mast. So we have to check all of these things to make sure we're uploading a safe and healthy plan. And it's really this obsession with repetition that is what makes NASA missions successful. And that's the theme that you're going to see in Apollo 13. At the beginning of the movie, you'll see the astronauts practicing again and again and again in the simulator. And it's that redundancy of checking and checking and checking and practicing before you do anything. That is really what makes NASA a success. Now, the very last meeting on here, at the very end of the day, that's actually at 2:15 a.m., that is the uplink. So that is the time when Mars is going to be in view of one of the Deep Space Network satellites, radio dishes. And so at that time, that is when the code that the scientists and engineers have been working on all day is going to get uplinked to the rover. So overnight for us, the rover will receive those commands and start executing them the next day. Okay, so Mars, the Moon, and the Earth, just showing you here how they look to scale. And you can picture, again, the immense distances between all of these. Now, just like you're going to see in Apollo 13, things go wrong. All the time, things go wrong on every space mission. And it's really that obsessiveness, obsessive attention to detail that allows us to work through them. So the first big problem that I was around to witness on the Curiosity rover mission was when the rover took a routine image of its own wheels, and the wheels looked kind of like this. So there are some holes in the wheels that are designed to be there, and the rectangular holes you see in the back of the wheels, those actually spell JPL in Morse code. A side story, NASA would not let the Jet Propulsion Laboratory put a JPL logo on the rover. So what the engineers decided to do, because they knew they needed to have these holes in the wheels so that dirt and small rocks wouldn't get trapped in there, they said, well, what if we just make these holes in a kind of asymmetric way, and they'll spell out JPL in Morse code. But the holes in the front of the wheels there, those were not supposed to be there. So Mars threw a surprise at us. Mars threw rocks at us that were sharper and pointier than rocks we had ever encountered on the surface of Mars before. These rocks are called ventifacts, which are rocks sculpted by wind. Some of these rocks might have been sitting on the surface of Mars for billions of years, potentially. And that's a lot of time with steady winds that can carve rocks on the surface into sharp little pyramids. So the rover wheel driving over a pointy, sharp little pyramid is just going to get punctured. These wheels were designed to be very thin to reduce the weight on the rover. So finding that the terrain was trying to destroy the rover was the first really big problem we had to deal with. And so we've been monitoring the wheels, and you can see how some of these specific holes have been growing over the course of the mission. So we're keeping an eye on these, and a piece of spacecraft nerd terminology that I'll give you is the term grouser, which is what we call the zigzag treads on the rover wheels. So the grousers are what really stabilizes the wheel, what we need to keep intact. And just last week, we saw that a couple of the grousers had started to be ripped. So this is a big deal. And what NASA does when something goes wrong on a mission, and that again that you'll see in Apollo 13, is they stop everything and throw all of their resources, all of their brain power at that problem. And what we did when we first saw that these wheels were in trouble was we stopped driving immediately. The rover is not going to drive until we figure this out. There's a huge mountain several kilometers away we need to get to. That's the whole point of the mission, but we're going to stop and throw all of our resources at this. We're going to have people model the strength of the wheels. We're going to have people go to the rover test bed, take the test rover out, try and simulate the same rocks that are there on the surface of Mars, drive the wheels over them and see what happens, and come up with a technique that we can safely drive the rover and minimize damage to the wheels. So here's an example of what some of that testing looks like in what's called the Mars Yard. And this rover here, this is called the Scarecrow rover. It doesn't have a brain. So it doesn't have its own battery. It doesn't have any science instruments. But conveniently, it weighs about 3/8 of what the actual rover weighs. And that makes it roughly the same weight as our real rover is on Mars. So the pressure on these wheels driving over Mars-like rocks should be what our rover is experiencing on Mars. So after driving around, succeeding in ripping up the wheels in all sorts of different ways and reproducing the damage that we were seeing on Mars, the engineers found that you can minimize the pressure on the wheels if you just drive the rover backwards. So because of the way that the wheels are aligned in what's called the rocker bogie system, it actually puts the least amount of pressure on the back wheels if you're driving backwards over the rock than the pressure on the front wheels if you are pushing forward and driving over the rock. So Curiosity, for the past 2 years, has been driving backwards. And that's totally fine because the rover has cameras in front and it has a redundant set of hazard cameras behind it. So the rover can be seeing where it goes as it drives backwards. A more recent problem that's come up that the engineers at NASA are still dealing with every single day is a problem with the rover's drill. So Curiosity was a new next generation rover that was called the Mars Science Laboratory because it has an onboard chemistry lab. It has an X-ray diffractometer. It has an evolved gas analysis and mass spectrometer instrument set. And in order to analyze the surface of Mars with those instruments, we have to grab a piece of Mars, crush it up into a powder, and feed it into the rover instruments. So to grab that piece of Mars, the rover carries with it a drill to extract a drill core from the interior of the rocks on the surface. And that drill is at the end of the rover arm that you see up above. And it looks like this thing with the drill bit seen down below in the lower left. So that drill has, for the past year or so, been shorting out on us. It's been acting up. And the drill has two modes. It can either rotate, like what we call a rotary drill, or it can tap the rock in what we call a percussion mode. And so we've experimented with only using percussion, with only using a rotary-only mode, and everything that we've done, we still get that short and when the drilling still stops. So I can't tell you what the solution is because this is an anomaly that's actively being worked. And again, what does NASA do when there is a problem with its spacecraft? Nothing hasty. NASA pulls the emergency brake and throws all of its resources at the problem, because the health of the spacecraft, and in the case of Apollo 13, the health of the astronauts, is absolutely the most important thing. So recently, just in the past couple of weeks, we've gone from creating a science plan for the rover 5 days a week to creating a plan for the rover only 3 days a week. So that gives 2 full days out of the week when everyone involved in the mission can be fully devoted to this problem of figuring out what's wrong with the drill. So stay tuned. There will be continual press releases coming out as the team works on the problem and hopefully finds a solution sometime soon. So those are some of the examples of my experience working with a NASA mission. And before we launch into the movie, I'd like to give you a few themes to look for in Apollo 13. And these are themes that really stood out to me as somebody who works with ongoing NASA missions. So the first theme that keeps coming up again and again in Apollo 13 that I'd like you to look for is this confidence that problems can be solved by clever people working hard. You'll see some examples of superstition in the movie. Gene Kranz has a lucky vest that he wears. Jim Lovell's wife loses her wedding ring only on, and that's a bad sign. But for the most part, the movie is an ode, a love story to the rational engineering mind, that any problem that comes up can be solved by clever people working hard. So one of the heroes of this story is the flight director, Gene Kranz, played by Ed Harris in the movie, and he has a few lines that kind of sum this up. When they first realize that there's a big problem on Apollo 13, he says, "Wake up everyone you need, get them in here, let's work the problem, people." There's this constant emphasis on working through the problem and this faith that it can be solved. He says, "I don't care what anything was designed to do, I care what it can do." So pushing the limits, figuring out what is the possibility that we can figure out. And then when there's a problem with the carbon dioxide filter, they have to literally figure out how to put a square peg in a round hole. And for those of you who love that scene in this movie, as you're watching it, if you're like, whoa, that's really cool, they figure out how to put this square peg in a round hole using only this box of crazy stuff on the spacecraft. If you love that scene, you're going to love the movie The Martian. It's pretty much that scene for an hour and a half. So check it out. One thing I'll note here, a little aside, this gentleman in the lower right, this is an engineer, John Aaron, and you're going to hear a mention in the movie to a steely-eyed missile man. This is the original steely-eyed missile man. He was an engineer on the Apollo 12 mission. When Apollo 12 was launching, in the process of exiting the Earth, it was struck by lightning. And this was the engineer who figured out how to restore its telemetry problems. And so he was the one who allowed Apollo 12 to complete its launch without just seconds before they were going to have to make the call to abort the mission. So he earned the title Steely-Eyed Missile Man. You're going to hear that again in Apollo 13. And if you watch the movie The Martian, you're going to hear another reference to the Steely-Eyed Missile Man. So that's where that comes from. Okay, another theme that comes up again and again in the movie that I'd like you to look for is that Apollo 13 is the beginning of the end of the Apollo era. And this is made clear to us very early in the movie when some VIPs, I believe this is Senator, asks Tom Hanks' character, why are we continuing to fund these programs now that we've beaten the Russians to the moon? We've done it. We landed a man on the moon. Why should we keep throwing money at this? What's the point? That is something that keeps coming up again and again in the movie, and it feels like it's being over-dramatized. It feels almost as if it's excessive in this movie, but it is real, and I think we and history tend to forget that the public was all too willing to let this era end very quickly. And one man in particular was more than eager to end the Apollo era, and that was the president at the time, Richard Nixon. So there's a lot of good documentation of Nixon's, I wouldn't say dislike, but lackluster support for the Apollo program, which was really President Kennedy's legacy. So Nixon, when he took office, it's documented in this photograph here on the left that there was a picture of the famous Earthrise from the Apollo 8 mission in December 1969. On the right is a picture of the same part of the Oval Office, again in April 1970. So that was around the time of the launch of Apollo 13, and that Earthrise picture has already been removed. So Nixon was not one to really feel a love for space exploration and the calling of the beyond. But we don't have to look at obscure evidence from these photographs to really know that. Nixon said as much. So in 1971, Nixon told an advisor he supported the space program because it was, quote, exploring the unknown. But he added, quote, I don't give a damn about space. I am not one of those space cadets. So this is the president, the only president who has his name on every lunar manned mission. So this is, keep this in mind when you watch the movie and you see all these hints about the beginning of the end. Now, another piece of trivia is that the near disaster of Apollo 13 spooked Nixon. And he, at that point, after Apollo 13, pushed to have the Apollo 17 mission, which was then in the works, he pushed to have that mission delayed until after the election. So he was kind of spooked about the potential disasters and bad visibility for himself in space. Now, what about the public? We tend to have a bit of a revisionist history in remembering the 1960s and the Apollo era as a time when the majority of people were excited about space and about our future as a spacefaring race. But the public polling data from the 1960s and 70s and beyond shows that that was never the case. So in the blue bars here, you see people who favor the US government sending human trips to the moon. And in red, you show those opposed. So in April 1970, around the time of Apollo 13, we had more than 50% of the population opposed to government spending for the Apollo program. So you're really going to see that in this movie, that this sense that this is our last gasp in space. And we have not been back to the moon since. Humans have not left low Earth orbit since the Apollo era. When I meet conspiracy theorists who try and convince me that humans never landed on the moon, that it was all in a television studio, the only good argument I have ever heard that I can't fully debunk from a conspiracy theorist is the argument that, well, if we did it in the 60s, at a time when a computer filled up the size of this room, why haven't we gone back? Why haven't we gone back with all these advances in modern technology? If we could do it then, why aren't we doing it now? And the reason is really, we've just decided not to. But the third theme here, I want to end on a hopeful note. The theme that space is awe-inspiring. And I mean that literally. Space inspires awe. And I think that if it does not inspire awe in you, what you see in this film, then please check your pulse, because this is the, I would question your humanity if you do not get some sense of awe in the glimpse of space, in the glimpse of the potential of human exploration that we see in this movie. So the movie starts out with the landing of Apollo 11. Neil Armstrong, first astronaut on the moon. And it's an interesting scene because this is the reaction of our hero, astronaut Jim Lovell, and his son while they're watching this first human on the moon. There's not a bunch of screaming, clapping, cheering, jumping up and down. It's a quiet scene. It's a sense of reverence. Just out of curiosity, who in this room remembers watching the first moon landing live? Someone want to just shout out what that experience was like? Was it a quiet moment, or were you cheering and clapping and jumping up and down? It was quiet. Yeah, that's interesting. Then hopefully this scene is something you will that will register with you and resonate with you. Tom Hanks gives a good line. He says, "It's no miracle. We just decided to go." And that's really true. It's not a miracle. It's not something superhuman. It's within us. It's something we decided to do, and with the power of the human mind, we did it. So when I imagine if I had been alive to watch this scene and to be part of that, my reaction would have been a little more like this. But the movie is very reverent, and it takes it seriously, and it gives this moment its due justice. And afterwards, there's a really sweet scene with astronaut Lovell and his wife lying out in their backyard in Houston looking up at the moon. And Tom Hanks gives the line, "From now on, we live in a time when men have walked on the moon." So I imagine that many, many generations beyond in history, those historians will look back on the past couple centuries and might distinguish major events by whether they happened before men have walked on the moon or after. I think that's a really serious and important step in our progress as human beings. So what Tom Hanks is doing here in this scene is he's covering up the moon with his thumb. And there's a nice parallel scene later on when he's in the spacecraft on the backside of the moon, emerging from the backside of the moon, looking at the Earth, and he reaches out and he covers the Earth with his thumb. I like that scene because it reminds me of something we've done with the Curiosity rover. You know, we've taken many, many pictures, astronomical pictures, amateur photos of Mars as seen in the night sky on Earth. It's a very bright, red, glowing dot. But our rovers have turned their cameras back on us. And you didn't know that you were being photographed, but you are part of that little blue dot there, one of those 2 or 3 pixels of blue light that the rover captured. So think about that when you watch those scenes and the parallels between looking at the moon from Earth and Earth from the moon. Think that we are doing that on a much larger scale with our robot explorers on Mars. Now, what I really like about Apollo 13 is that it also makes the moon feel like a place. There's some nice scenes of astronauts on the moon. There's some beautiful scenes of the astronauts looking from the window of the spacecraft at the spectacular geology passing underneath them on the surface of the moon. And our rovers have really given us that same sense that Mars is not just a planet, but a place, a world. And we can see the tracks that the Spirit rover had made in 2006 in this image here. And there's a part in the rover's wheel track here that looks very familiar to me. I'm going to zoom in on this. And I'm just going to leave you with this parallel here. So we do have footprints of a sort on Mars. So please keep those things in mind when you're watching the movie. And I really hope that this is a joyous and thrilling experience watching this movie together on a big screen with a great sound system. So I'm happy to take a couple of questions before we start the screening. Yeah. Okay, great question. So the question was, if we are seeing Earth from Mars and the atmosphere is so thin, why don't we see other stars around? And the reason is that viewing the Earth from Mars is like viewing Venus from the Earth, because it's the next planet closer to the sun, which means that the Earth, when viewed from Mars, is always fairly close to the sun. So the only time we can really see Venus from Earth is in the morning or evening. Sometimes Venus is called the evening star because it's only right after sunset that you see Venus, because Venus is so close to the sun that then it shortly afterwards follows the sun and dips below the horizon. So on Mars, the Earth is a morning star and an evening star. And what you're seeing with this bluish light here is the haze of a Martian sunset. Sunsets are blue on Mars. And so very shortly, after the sun has set here, you can see Earth in the dim glow of the Martian sunset. And then by the time it gets dark enough to see stars out towards the horizon, the Earth will have set below those mountains that you can see. Good question. Yeah. Aside from curiosity, why is there so much focus on the exploration of Mars? Well, I went through this whole rigmarole to show you how far away Mars is. But in terms of space exploration targets, Mars is super close. It only takes us 7 to 9 months to get to Mars. It takes us a decade to get to the outer solar system, to get to places like Jupiter, Saturn, Pluto. So for Mars, we can launch something to Mars with a really favorable orbital alignment of the Earth and Mars in just the right spot every 2 years. So that's why we get something sent to Mars about once every 2 years. But it has to be such a larger effort to get something way beyond. And aside from that, Mars is just cool. You know, Mars is a place that's very Earth-like. The public can get excited about these landscapes that are very similar to our own experience on this planet. And most intriguingly, Mars did not look like this in its past. Mars would have looked a lot more Earth-like. It would have had rivers. It would have had rain and snowfall and glaciers. Mars early on was a much more Earth-like place with Earth-like conditions. And the big questions we have for Mars now are, did Mars evolve life very early on when it had conditions that we think were like the conditions where life evolved on the early Earth? So there's a lot of motivation to send our spacecraft to Mars to look for clues about life. And that gets at the big questions, the big philosophical questions of, are we alone? So that's what we're searching for on Mars. Yeah.
Wouldn't the temperature on Mars, the atmosphere, be a little hotter because it's farther away from the sun and doesn't get as much heat?
What about the temperature on Mars? So Mars is 1.5 times further from the sun than the Earth is. So Mars gets less sunlight. It also has so little atmosphere. It doesn't have enough atmosphere to have a greenhouse effect to keep the surface nice and warm like we do on the Earth. So Mars is actually a very, very cold place. The warmest temperature we've ever read on the surface of Mars with our rovers is about 20 degrees Celsius, and that is like a hot tropical day. Most of the time, we're talking minus 70 to 100 degrees. So super cold on Mars. Yeah.
So you mentioned the one question from people that say we didn't go to the moon that stumped you that you couldn't answer. When you meet people like that, what's your best retort? What's the best answer to say, yes, we did go to the moon?
There are specific arguments you can give for the kind of classic arguments for why we didn't land on the moon. Things like the flag was waving. How does a flag wave if there's no atmosphere on the moon? Well, it's inertia. You plant a flag and there's going to be some momentum and vibrations in the flag. So there's an answer like that to all of the classical ones. But just for the general, what do I say for someone who doesn't think we landed on the moon? I say, wouldn't you rather live in the world where humans did accomplish this? Wouldn't you rather be living in the era where from now on men have walked on the moon? Why would you go through these mental contortions and create these straw man arguments to live in a different reality that where you're not part of a humanity that has accomplished something so exciting? Yes, sir.
Speak of 2020, what about this administration and the funding?
Well, fortunately, it appears that this administration thinks that NASA is a good way to make America great again. And so even though NASA has been subject to funding cuts, as pretty much every government agency apart from defense has, our cuts have been no larger in the proposed budget than they were during the Obama administration. So NASA seems to be off the hook, including the Earth Science Division of NASA. There are still cuts that are going to be painful, but nowhere near to the extent that the other agencies, especially the National Institute of Health and EPA, have been slashed. Yes?
How much
influence has the private sector have on space exploration now, especially to Mars?
Yeah, the private sector is having a huge influence. Elon Musk, in particular, with SpaceX, has been doing a tremendous amount just to get the public excited about the possibility of space again, with making the goal of getting 1 million people to Mars. And so the role of the private sector is really invigorating the public. It's also making rocket launches cheaper, creating some competition. But keep in mind that SpaceX essentially works for NASA. Without NASA proposing these big visions for missions, SpaceX Blue Origin would be out of a job.
One comment real quick. I was at Kennedy Space Center 2 weeks ago in Cape Canaveral. So I saw a Saturn V rocket, which is used in the Apollo missions.
Yeah.
And saw Launch Pad 39A, which was used in some of the Apollo launches, which is so super inspiring to be there, see it in person.
Yeah, definitely.
Yeah, and it's the rocket is just gigantic.
Oh, I know, it's incredible. So let me actually show you the Saturn V rocket to scale, because the Saturn V is really one of the heroes of this movie as well. So the Saturn V is the second from, on the far right here. So it's about as tall as Big Ben, dwarfs the Statue of Liberty. And we just had a question about SpaceX. The giant rocket that SpaceX is working for, the Falcon Heavy, is third from the left there, and the Saturn V still dwarfs it. NASA's next big rocket that it's building to go back to the moon and beyond is called the Space Launch System, and that still is not going to be as big as the Saturn V was. So yeah, I strongly encourage anyone with an interest in space exploration to go to one of the 3 locations where the unused Saturn rockets are. So one was the Kennedy Space Center in Florida, one is in Alabama, and the third is in Johnson Space Center in Houston. And it's not until you go and you see the size of this thing for yourself that the power of what you're going to see in the launch scene in Apollo 13 really rings true. This is an absolutely amazing feat. And the 3 Saturn V rockets that we have on display are here on Earth on display because Nixon canceled the Apollo program early. So those were all built to launch to the moon, and they never got a chance. If there are any screenwriters out there, I'm going to give you a gift. I have this great idea for a movie. So for some reason, you got to go save someone on the moon or Mars or something, and there's no rocket ready. So Tom Cruise or Bruce Willis or whoever your star is goes and gets one of the old Apollo Saturn V rockets, fuels it up, and launches it into space. Could happen. All right, well, let's end it there so you can have a short break to stretch your legs, grab some popcorn, and then we can begin our movie.